Hi, my name is Elise. I am 14 years old, and I am here to explain to you Fermat's last theorem. It started a long time ago when a mathematician named Fermat was looking at an equation. A to the n plus b to the n equals c to the n. When n was equal to 2, it created the Pythagorean theorem, also known as a squared plus b squared equals c squared, where a was a side, b was a side, and c was the hypotenuse of a right triangle. Let me demonstrate this with cheese. We start out with the right triangle. Then we go on to say that a sliver equals 1 and a square equals 1 squared. So let's give this triangle side lengths and do an example. Side A equals 3, side B equals 4, and we are trying to find side C. Let's start by giving A side 3 slivers and the B side 4 slivers. Then we'll consult our equation. And the equation is a squared plus b squared equals c squared. So our next step, according to the equation, is to square sides a and b. So 3 times 3 is 9, so we'll give that a 9. And side b is 4 times 4. So 4 times 4 is 16, so we'll give that 16 squared. So here we have 9 being a squared, 16 being c squared, still trying to find c. But according to the equation, c squared is 9 plus 16, or a squared plus b squared, which equals 25. So now we know what c squared is supposed to be, but in order to find c, we have to square root it. So let's fill in this hypotenuse with the c squared, so 25. In order to find square root, we have to take away all the extra squares, and that leaves us with 5, so c equals 5. So what we know now is that Pythagoras' theorem is a squared plus b squared equals c squared. But Fermat said, what if n is equal to something greater than 2, such as a cubed plus b cubed equals c cubed, or a to the fourth plus b to the fourth equals c to the fourth? Fermat's last theorem became known as whether or not a to the n plus b to the n would equal c to n when n was greater than 2. So no one knew how to solve Fermat's last theorem, so they decided to try using computers. They would plug in n with every number imaginable, and this worked for a little while, until realization came upon them. There was an infinite amount of numbers, so no matter how many numbers got tested, there was still infinitely left, which meant that in order to solve Fermat's last theorem, there had to be a proof. To begin, what is a mathematical proof? The basic version is when a conjecture is proven to be true without having to solve every problem. An example would be the Pythagorean theorem proof. So what is a conjecture? A conjecture is basically an idea in math that hasn't been proven yet. The proof of Fermat's last theorem began to be solved by a guy named Andrew Wiles. He began studying elliptic curves. An elliptic curve is a series of equations whose answers form the shape of a donut. So every point on this donut is equal to that of equation. So while Wiles was studying elliptic curves, 2 Japanese mathematicians halfway across the world were studying modular forms. So what are modular forms? Modular forms are functions on the complex plane that create completely symmetric shapes. They are so symmetrical that many people believed they didn't exist. They were proven to exist, though. So what is a function? It's basically just an equation with variables. And what is a complex plane? A plane where complex numbers lie. And last, what are complex numbers? They are imaginary numbers which are represented by the letter I. Imaginary numbers are numbers whose squares are negative, which is impossible because every negative times a negative is a positive. A complex number is an imaginary number that is in an equation with a real number. For example, 5 minus I, or 5 times I, or 6 plus I, or 6I. So to restate, Modular forms are functions on the complex plane that create so much symmetry they are impossible to see with the eye. Here is my representation of a modular form. Getting back to the two Japanese mathematicians. Their names were Tomiyama and Shimura, and they came up with a conjecture together. They said that every elliptical curve is actually a modular form. This became known as the Tomiyama-Shimura conjecture. At one point, there was a guy named Fry who had heard of this conjecture and Fermat's last theorem, and he said, what if we make n imaginary? If this created an equation that were true, it would create an elliptic curve so weird it wouldn't be modular anymore. This idea became known as the epsilon conjecture. It was later proved by another mathematician. So Andrew Wiles took this newly proved epsilon conjecture and related it back to Fermat's last theorem. His goal now was to count all the elliptic curves of the equation to see if they were all modular. But since there were infinitely many, he couldn't count them all. The theory was that if Tomiyama-Shimura were correct, so was Fermat's last theorem, and vice versa. Wiles then converted the elliptic curves into Galois representations. Galois representations would make elliptic curves in modular forms easier to count. So now we have our elliptic curve becoming a Galois representation. Since modular forms and Galois representations or elliptic curves became grouped together, it made it easier to count them, meaning he could count every elliptic curve or Galois representation that was in modular form. At one point, he got stuck counting, and he decided, if I switch counting from one number to another number, it'll make it easier to count. That was the last step to completing Fermat's last theorem. It was solved or proved by Andrew Wiles in 1995. Thanks for watching.